Imagine waking up tomorrow and realizing that every choice you never made was made somewhere else. Somewhere, another version of you chose a different path, spoke different words, lived a different life. This may sound like science fiction, but modern physics tells us something astonishing. The existence of parallel universes is not fantasy. It may be a direct consequence of the laws of nature themselves. Tonight, we're going to peel back the curtain of reality and explore one of the most radical ideas ever proposed by science, that our universe may be just one bubble in a vast cosmic multiverse. That for most of human history, we believed the universe was everything. One cosmos, one set of stars, one unfolding story from beginning to end. This idea feels natural because our senses are limited. We see a sky filled with galaxies and assume that is the whole stage on which reality plays out. But physics has an uncomfortable habit of shattering comfortable assumptions. When scientists began writing down the equations that describe the universe with precision, something unexpected happened. The mathematics refused to settle on a single solution. Instead of pointing to one inevitable universe, the equations allowed many. And when nature allows many solutions, physics teaches us that nature often chooses all of them. This is where the idea of parallel universes quietly enters the conversation, not as philosophy or fantasy, but as a logical consequence of how reality seems to operate at its deepest level. The problem begins with a simple question: why does our universe look the way it does? The laws of physics appear exquisitely tuned. Gravity is weak enough for stars to burn for billions of years, yet strong enough to form galaxies. The constants of nature fall into a narrow range that allows atoms, chemistry, planets, and eventually life. If these values were altered even slightly, the universe would be sterile or short-lived. For decades, physicists struggled with this mystery. Was this tuning intentional, accidental, or the result of some deeper principle yet to be discovered? As theories grew more sophisticated, particularly in cosmology and particle physics, an unsettling possibility emerged. Perhaps the universe is not finely tuned at all. Perhaps we are simply living in one of many universes, and we observe these life-friendly conditions because only such universes can host observers in the first place. This idea radically reframes our place in reality. Instead of asking why the universe was designed for life, we begin to ask, how many universes exist where life is impossible, silent, or fleeting? Our universe may not be special in its existence, only in its habitability. Just as Earth was once thought to be the center of creation before we learned it is one planet among billions, our universe may be one cosmic address among countless others. This is not a demotion of humanity, it is an expansion of perspective. It suggests that reality is vastly larger than the visible cosmos, and that what we call the universe may be only a smaller region of a much grander structure. This shift becomes even more compelling when we move from the large-scale universe to the smallest scales of existence, where quantum mechanics reigns. At this level, reality behaves in ways that defy common sense. Particles do not have definite positions or states until they are observed. Instead, they exist as clouds of probability, capable of being in many states at once. A particle can spin clockwise and counterclockwise simultaneously, pass through multiple paths at the same time, and interfere with itself as if it were many particles rather than one. This is not metaphorical language. It is how nature behaves, confirmed again and again by experiment. The question that haunted physicists was simple but profound. When a quantum event has multiple possible outcomes, how does nature choose which one becomes real? One interpretation suggests that nature makes a random choice, collapsing the wave of possibilities into a single outcome. But there is another interpretation, equally consistent with the mathematics and far more radical in its implications. According to this view, nature does not choose. Instead, all outcomes occur. Reality splits. In this framework, every quantum event causes the universe to branch into multiple versions of itself. In one branch, a particle goes left. In another, it goes right. In one universe, a radioactive atom decays. In another, it does not. Each possibility becomes real in its own self-contained universe. These universes do not communicate, but they coexist, layered atop one another like transparent sheets of reality. What we experience as randomness is simply our movement along one branch of a constantly branching multiverse. This idea transforms parallel universes from speculative cosmology into an unavoidable implication of quantum mechanics. It means that the universe is not a single unfolding story, but a vast library of stories all written simultaneously. Every choice, every interaction, Every moment of uncertainty gives rise to new branches of reality. The universe is not economical, it is extravagant. It explores all possibilities, not just one. At first, this idea seems overwhelming, even unsettling. It challenges deeply held intuitions about uniqueness, identity, and causality. Yet, the mathematics of quantum theory does not flinch. The equations evolve smoothly and deterministically. There is no sudden collapse, no arbitrary selection. The branching of universes is not an added assumption. It emerges naturally when the equations are taken seriously. In this sense, the many worlds picture is not the wildest interpretation of quantum mechanics. It may be the most conservative, because it adds nothing to the equations themselves. This also resolves one of the oldest puzzles in physics, the role of the observer. In traditional interpretations, observation appears to have a mysterious power, collapsing possibilities into facts. But in a branching universe, observation is simply interaction. When you observe a quantum event, you become entangled with it. You split along with the universe, experiencing one outcome, while other versions of you experience the alternatives. Consciousness does not create reality. It follows it. The implications ripple outward into our understanding of existence itself. Somewhere in another branch of reality, different outcomes unfolded. Decisions went another way. Histories diverged. This does not diminish the meaning of our experiences. It intensifies them. This universe, the one you inhabit, is the only one you will ever experience. Its joys and struggles are real precisely because they are lived, not because they are unique among all possibilities. What makes this picture even more astonishing is that it aligns with what we already know about quantum experiments. Interference patterns, entanglement, and the stability of quantum systems all make sense in a universe that never collapses, only branches. The mathematics works with extraordinary precision. The universe, it seems, is not committed to simplicity in the way the human mind prefers. It is committed to consistency. When we combine this quantum view with cosmology, the picture grows even larger. Inflationary theory suggests that space itself may be spawning new universes continuously, each with its own physical properties. Quantum mechanics suggests that reality branches at every moment. Together, they paint a picture of existence that is almost beyond comprehension, a vast multiverse where universes are born, split, and evolve endlessly, governed by elegant equations that operate without preference or intention. This does not reduce humanity to insignificance. On the contrary, it places us inside one of the most extraordinary structures ever conceived. We are not observers standing outside reality. We are participants embedded within it. Our universe is one thread in a cosmic tapestry, and our experiences are the way the tapestry becomes aware of itself. Parallel universes, in this sense, are not an escape from reality. They are an invitation to understand it more deeply. They show us that the universe is not constrained by human intuition, that nature is free to explore every possibility permitted by its laws. And as our understanding grows, so too does our sense of wonder. The universe is not only stranger than we imagine, it is stranger than we can imagine, and yet governed by principles so precise that we can glimpse them through mathematics, experiment, and thought itself. To truly grasp the idea of parallel universes, we have to zoom out far beyond galaxies, beyond clusters of galaxies, beyond even the observable edge of our cosmos, and ask how the universe itself was born. Modern cosmology tells us that the universe began in a tiny, hot, dense state and then underwent an event of almost unimaginable violence and speed. In a fraction of a second, space itself expanded faster than the speed of light, stretching microscopic regions to cosmic scales. This process, known as inflation, explains why the universe looks so smooth, so uniform, and yet seeded with the tiny imperfections that would later grow into galaxies, stars, and planets. But inflation, when taken seriously, leads us somewhere astonishing. It suggests that the universe we see may not be the only product of this expansion, and perhaps not even the most typical one. The equations describing inflation do not require it to happen once and then stop everywhere. In many versions of the theory, inflation is eternal. While it ends in our region of space, allowing matter, energy, and time as we know them to emerge, it continues elsewhere. Space keeps inflating in distant regions, endlessly, relentlessly, creating new pockets of space where inflation eventually shuts off. Each of these pockets becomes a universe in its own right. Our universe, with its 13.8 billion years of history, may be just one bubble in an infinite. Cosmic foam constantly spawning new universes beyond our observable horizon. This idea changes the meaning of the word cosmos. What we once called the universe may be more accurately described as a small island in a vast multiversal ocean. Each bubble universe is born with its own initial conditions, its own arrangement of energy, and potentially its own laws of physics. From the inside, each universe appears complete and self-contained. Observers within it see a horizon, a beginning, and a consistent set of rules. Yet from a higher perspective, all these universes are connected by the same underlying process that gave birth to them. This framework offers a powerful explanation for one of the deepest mysteries in science: why the constants of nature take the values they do. The strength of gravity, the mass of the electron, the charge of the proton. The rate at which the universe expands, these numbers appear arbitrary. Physics can describe them, but it struggles to explain why they are what they are. In a multiverse born of inflation, these constants may vary from universe to universe, determined by random processes during their formation. Most universes would be hostile to complexity. Only a small fraction would possess the delicate balance required for stars, chemistry, and life. We find ourselves in one of those not because it was destined, but because it was necessary for our existence. This perspective does not diminish the beauty of our universe, it enhances it. It suggests that the universe is not finely tuned by coincidence or design alone, but selected through a vast cosmic process. Life emerges not because the universe was guaranteed to support it, but because reality explores every possibility, and life arises where conditions permit. In this view, our universe is both ordinary and extraordinary ordinary in its existence, extraordinary in its capacity to host conscious beings, capable of reflecting on the cosmos. Now consider what this means when we look at the laws of physics themselves. We often assume that the laws of nature are universal and immutable, written into the fabric of reality. But if multiple universes exist, there is no guarantee that they all share the same rules. In some universes, the electromagnetic force might be stronger, binding electrons so tightly that chemistry as we know it becomes impossible. In others, gravity might dominate, causing matter to collapse before stars can stabilize. Some universes might expand so rapidly that matter never clumps together at all, remaining forever dark and empty. There could even be universes with extra dimensions of space, curled or extended, in ways that radically alter the behavior of particles and forces. In such realities, atoms might be unstable, time might behave unpredictably, or the concept of cause and effect might differ from our own. The familiar structures we rely on, atoms, molecules, DNA, are not guaranteed features of reality. They are local achievements, the result of a specific set of physical rules that happen to operate here. This idea forces us to confront a humbling truth. The laws we consider fundamental may be environmental. They may be the local conditions of our cosmic neighborhood rather than universal truths that apply everywhere. Just as the laws of chemistry differ between Earth and Jupiter due to environmental conditions, the laws of physics themselves may differ across the multiverse. What we call fundamental may simply be what holds true in our particular bubble universe. Yet even within this vast diversity, there may be a deeper order. Many physicists believe that beneath all these varied laws lies a single underlying framework, a master theory that allows for many possible universes. The multiverse would then be the natural expression of that deeper theory, just as countless snowflakes are the natural expression of the laws of crystallization. Each snowflake is unique, yet all are governed by the same fundamental principles. This raises profound questions about predictability and explanation. If the laws of physics vary across universes, what does it mean to explain anything at all? In a multiverse, explanation shifts from inevitability to probability. Instead of asking why the universe must be this way, we ask why it is likely to be this way given the broader landscape of possibilities. Science does not lose its power in this shift, it adapts. It becomes a tool for mapping not just one reality, but the space of all possible realities. For some, this idea feels unsettling, as though it robs the universe of meaning. But meaning does not vanish when uniqueness disappears. A sunset is not less beautiful because there are countless sunsets across the cosmos. A human life is not less valuable because billions of humans exist. Meaning arises from experience, from participation, from being embedded within a story. Our universe remains meaningful because it is the one we inhabit, the one in which our history unfolded and the one in which our future will be written. What is remarkable is that these ideas did not emerge from imagination alone. They arose from equations written to explain real observations, the distribution of galaxies, the temperature of cosmic radiation, the behavior of particles in accelerators. When physicists followed those equations without flinching, they were led to conclusions that stretched the limits of intuition. The multiverse was not invented to be strange, it was discovered to be unavoidable. In this light, parallel universes are not an escape from science, but its ultimate expression. They represent the willingness to accept what the mathematics implies, even when it challenges deeply held assumptions about reality. They remind us that the universe is under no obligation to conform to human expectations. Nature is free to be vast, prolific, and astonishingly creative. And perhaps that is the most profound lesson of all. The universe is not a static stage built for a single performance. It is a dynamic, generative process, continuously producing new worlds, new laws, and new possibilities. Our universe is one verse in a cosmic poem still being written, and our role is not to stand apart from it, but to understand it as deeply as we can, using reason, imagination, and the quiet courage to follow the evidence wherever it leads. When people first encounter the idea of parallel universes, the question that immediately follows is not about equations or telescopes, but about themselves. If multiple universes exist, what does that say about choice, destiny, and free will? Are our decisions meaningful if every alternative happens somewhere else? This question cuts to the heart of human identity, and surprisingly, physics has something profound to say about it. The existence of parallel universes does not erase choice, it reframes it. Each decision you make still matters, not because it eliminates other possibilities, but because it defines the reality you experience. You are not diluted by the existence of other outcomes, you are anchored to the one you live through. In a branching universe, the future is not a single road stretching forward, but a constantly unfolding tree of possibilities. At each moment, quantum uncertainty allows multiple outcomes, and reality accommodates all of them by branching. But from your perspective, only one branch is real. You feel the consequences of your actions because you inhabit the branch shaped by those actions. Responsibility does not vanish in a multiverse. It becomes localized. The fact that another version of you may exist elsewhere does not comfort you if you fail here, nor does it diminish success if you achieve it. Meaning arises from experience, not exclusivity. This perspective challenges the classical idea of fate. In a deterministic universe, the future is fixed, written into the past like ink that cannot be erased. In a branching universe, the future is open, rich with possibility, yet structured by probability. You are not a passive observer drifting along a predetermined timeline. You are an active participant moving through a landscape of possibilities, constrained by physical laws but not scripted by them. Free will, in this sense, is compatible with physics not because outcomes are unrestricted, but because multiple futures are allowed, and you inhabit one through action and interaction. This also reframes how we think about failure and regret. In everyday life, regret arises from imagining paths not taken. In a multiverse, those paths may actually exist somewhere else, but this does not trivialize regret, it deepens it. Regret is not about the literal existence of alternatives, but about the meaning of the path you chose. Knowing that another version of events may have unfolded elsewhere does not erase the emotional weight of this one. If anything, it highlights how precious each lived moment is. This universe, this branch, is the only one you will ever experience. Parallel universes also offer a new lens through which to view creativity and innovation. Every great idea begins as a fragile possibility, one among many. In a universe that explores all possibilities, creativity is not an anomaly. It is a natural expression of cosmic abundance. Human imagination becomes a reflection of the universe's own generative power. When you imagine a future different from the present, you are not merely fantasizing. You are intuitively grasping the branching nature of reality. Visionaries do not create possibilities from nothing. They recognize which branches are worth pursuing. Yet as seductive as these philosophical implications are, science ultimately demands evidence. This brings us to the most controversial and challenging question of all: can parallel universes ever be tested, measured, or proven? Critics argue that if other universes cannot be observed, they fall outside the domain of science. This concern is not trivial. Science progresses by making predictions and comparing them with observations. A theory that cannot even in principle, be tested risks drifting into metaphysics. But history reminds us to be cautious before dismissing unseen realities. Atoms were once invisible, dismissed as convenient fictions. Black holes were once mathematical curiosities, doubted even by those who derived them. Gravitational waves were once thought too weak to ever be detected. In each case, indirect evidence came first. Subtle effects, unexplained anomalies, and precise measurements gradually revealed the presence of something real but unseen. Parallel universes, if they exist, may leave similar fingerprints on our universe. One possible clue lies in the structure of cosmic background radiation, the faint afterglow of the Big Bang. This radiation carries information about the earliest moments of the universe. If our universe collided with another in its infancy, it could have left a detectable imprint, a subtle scar in the pattern of temperature fluctuations across the sky. Scientists have searched for such anomalies not as proof, but as hints that our universe may not have evolved in complete isolation. Another avenue involves gravity itself. Gravity is uniquely sensitive to the structure of space-time. Some theories suggest that the effects of other universes could influence gravity in ways we have not yet fully understood. Tiny deviations from expected gravitational behavior, especially at cosmic scales, could hint at dimensions or realities beyond our own. These effects would be extraordinarily subtle, requiring instruments of immense precision and patience measured in decades. Quantum mechanics also offers potential windows into the multiverse. The branching interpretation of quantum mechanics makes specific predictions about how quantum systems behave, especially in terms of coherence and interference. Experiments that push quantum systems to larger and more complex scales test whether quantum behavior truly persists without collapse. Each successful experiment that preserves quantum coherence strengthens the case for a universe that does not choose a single outcome but allows all of them to coexist. There is also the role of mathematics itself. In physics, mathematical consistency is not optional. Theories that describe reality must fit together without contradiction. When different branches of physics independently point toward the existence of multiple universes, this convergence matters. Quantum mechanics suggests branching realities. Inflationary cosmology suggests multiple bubble universes. String theory suggests a vast landscape of possible physical laws. These ideas were not designed to support one another, yet they intersect in a way that is difficult to ignore. Of course, skepticism remains essential. Science advances not by belief, but by doubt sharpened into inquiry. The multiverse may turn out to be incomplete, revised, or replaced by a deeper theory we have not yet imagined. But even this possibility is instructive. It reminds us that science is not a finished book, it is a living process. The willingness to entertain bold ideas while demanding rigorous evidence is what drives progress. What is remarkable is that the multiverse, if real, does not reduce science to chaos, it does the opposite. It imposes structure on apparent randomness. It explains why the universe appears finely tuned without invoking mystery or intention. It unifies quantum mechanics and cosmology under a common narrative of abundance rather than scarcity. Reality, in this view, is not stingy, it is generous beyond comprehension. And perhaps the deepest implication is this: the universe is not built around us, but it is not indifferent to us either. We are expressions of its laws, patterns of matter and energy that have become capable of reflection. In exploring the possibility of parallel universes, we are not escaping reality. We are expanding our understanding of what reality can be. We are learning that existence is not a single thread, but a vast tapestry woven from countless possibilities, each as real as the one you are experiencing now. As the idea of parallel universes matures from speculation into serious scientific discussion, attention naturally turns toward the future, not just the distant cosmic future, but the future of human knowledge and technology. If multiple universes exist, separated by barriers of energy, dimension, or space-time itself, could an advanced civilization ever interact with them? According to everything we currently know, such feats lie far beyond our capabilities. The energies required would rival those present at the birth of the universe. Yet history warns us against confusing impossible today with impossible forever. Every major technological revolution began as an absurdity. Flying machines, nuclear energy, and space travel were once dismissed as fantasies, not because they violated physical laws, but because humanity lacked the tools to realize them. Modern physics already hints that space-time is not the rigid, passive backdrop it once seemed to be. It can stretch, curve, ripple, and perhaps even tear under extreme conditions. Wormholes, theoretical tunnels through space-time, arise naturally in Einstein's equations. Though wildly unstable with known physics, they suggest that space-time may be engineered under the right conditions. If parallel universes exist as regions of space-time separated by higher dimensions or quanta boundaries, then in principle, not in practice, there may be ways to bridge them. The obstacle is not law, but scale. The universe allows these structures, but demands a price measured in stellar energies. This realization reframes how we think about advanced civilization. A truly mature civilization would not be defined merely by its ability to harvest energy from planets or stars, but by its mastery of space-time itself. Such a civilization would view reality not as a fixed stage, but as a dynamic system to be navigated and reshaped. While this remains firmly in the realm of theory, it highlights an important point. The multiverse is not just an abstract concept. It sets the ultimate boundary conditions for what is physically possible. Yet, even if interaction between universes remains forever beyond reach, the multiverse still reshapes our understanding of reality in a profound way. It forces us to abandon the idea that existence is narrow, rare, or fragile. Instead, reality appears robust, prolific, and endlessly creative. Universes are born, evolve, and disappear as naturally as waves in an ocean. Laws of physics are not sacred commandments etched into eternity, but outcomes of deeper principles capable of generating countless variations. The universe is not a machine producing a single output. It is a generator exploring all allowed possibilities. This perspective alters how we think about beginnings and endings. In a multiverse, the Big Bang may not be the absolute beginning of everything, but a local event, the birth of our particular region of space-time. Likewise, the eventual fate of our universe-weathered expanse forever tears itself apart, or collapses may be only one outcome among many. Other universes may follow different trajectories, some ending quickly, others persisting far longer than ours. Reality does not converge on a single destiny. It branches endlessly. There is a deep philosophical resonance here. For centuries, humans searched for a final, ultimate explanation, a single reason why reality exists and why it is the way it is. The multiverse suggests the explanation may lie not in uniqueness, but in plurality. Reality may not require a single outcome to justify its existence. It exists because the laws that govern it allow existence in many forms. The question shifts from why this universe to why this framework of possibilities, and that question points us toward deeper laws still waiting to be discovered. What is striking is that this grand vision emerges not from mystical speculation, but from the careful extension of known physics. Quantum mechanics, general relativity, and cosmology, three pillars of modern science, each independently gesture toward a reality far larger than the visible universe. When independent theories converge on a similar conclusion, scientists pay attention. The multiverse is not embraced because it is comforting or dramatic, but because it may be the most honest reading of the evidence we have. This does not mean certainty. Science is built on humility. Every generation believes it stands near the summit of understanding only to discover that the mountain continues upward. The multiverse may be refined, reinterpreted, or even replaced by a deeper concept that renders it incomplete. But even if that happens, the lesson will remain. Reality is not obligated to fit within the limits of human intuition. The universe, whatever its ultimate structure, is more expansive than common sense would ever predict. And this brings us to the deepest insight of all. The value of the multiverse is not merely in its implications for physics, but in what it teaches us about ourselves. We are small but not insignificant. We are brief but not meaningless. In one universe among many, matter organized itself into atoms, molecules, stars, planets, and eventually minds capable of asking questions about existence. That alone is extraordinary. The universe did not have to produce observers, yet it did. And through those observers, the universe begins to understand itself. Parallel universes remind us that knowledge is not about comfort, it is about courage. The courage to follow equations where they lead. The courage to accept conclusions that challenge intuition. The courage to live in a reality that is vast beyond comprehension, yet still accessible through thought, experiment, and imagination. We may never visit another universe, but by understanding the possibility of their existence, we expand the boundaries of our own. In the end, the multiverse does not make reality colder or more distant, it makes it richer. It tells us that existence is not a fragile accident, balanced on a knife's edge, but a powerful generative process unfolding across unimaginable scales. And within that process, our universe is one luminous thread, our lives a brief but meaningful pattern woven into a tapestry far greater than anything humanity once dared to imagine. When we step back and look at the full picture, what emerges is not a cold or empty cosmos, but a reality far richer and more astonishing than we ever imagined. The idea of parallel universes tells us that existence is not limited to a single path or a single outcome. Instead, reality is generous, creative, and vast beyond comprehension. From the smallest quantum events to the largest structures in the cosmos, the universe appears to explore every possibility allowed by its laws. Our universe is not diminished by this truth, it is elevated by it. It becomes one precious expression of a deeper and more powerful framework that gives rise to countless worlds, histories, and futures. This perspective also reminds us of our unique role. In one universe among many, matter learned how to think, to question, and to wonder. Through science, we are not merely studying the universe from the outside, we are participating in its self-discovery. Each new insight expands the boundary of human understanding and reveals that the universe is far stranger, more elegant, and more beautiful than intuition ever suggested. Whether or not we ever prove the existence of parallel universes directly, the journey to understand them pushes science forward and deepens our appreciation of reality itself. Thank you to all the viewers for joining this exploration of the deepest ideas in modern science. Your curiosity is what drives discovery, and your willingness to question the nature of reality keeps the spirit of science alive. Stay curious, keep asking bold questions, and remember that the universe still holds more mysteries than we can imagine.